going to mini lecture on cosets of subgroups, and cosets are the analog of congruence classes modulo ideals that we saw in rings. So that's what I have written here. So let's start with a group G and a subgroup K. And we'll fix an element A in G. And so a coset, and I guess we're defining right cosets here, is a right coset Ka is defined to be the set of elements of the form K times A, where K is in the subgroup K. Okay, so this is the definition. It's what's written on your adventure sheet. But I like to think of this more visually. So if I think of this box here as the whole group G, and maybe this smaller box inside is all of K. Let's say that K contains the points E and K1 and K2. Maybe it contains other points, but let's just track these. What a coset does is it multiplies every element of K by A to get a new set of elements in G. So if I multiply E times A, I get EA. If I multiply K1 times A, I get K1A. If I multiply K2 times A, I get K2A. And by the way, I'm looking at right cosets, which means I'm always multiplying by A on the right. I could look at left cosets, which mean that I multiply by A on the left, but I shouldn't mix them. If I'm multiplying by A on the right, I stay on the right for everything. Okay, so I translate all of the elements of K to other elements of the group by multiplying by A. And so if I do this for everything in K, I get my set of elements called Ka. And then if I let B and C also be elements of my group, I could do the same thing for B. So I could take the coset KB, where I multiply everything in K, times B on the right. And I could do the same thing for C, K1C, K2C. And if I do this enough, I eventually get every element of the group. This is something that you'll prove on your adventure sheet, so I'm not going to give you a proof, but I'll state it now as a fact. Fact 1, every element of G is in some coset, some right coset of A. Okay. And then another fact is that every element of G is only in one right coset. These two facts together give us the definition of what it means to be our partition. So that is the cosets of G partition, or of K. So recall that a partition is a collection of sets, subsets, so that everything in my set is in exactly one of those subsets. But that's exactly what these two facts say, that every element of G is in exactly one coset of K. That's exactly what it means to be a partition, for the cosets to partition. Okay, so that gives us nice facts that we will prove on our adventure sheet, but I'd like to return to this picture and give a little bit more of the intuition that I have in terms of cosets. So I think of cosets as taking a copy of K, and when I multiply on the right, I'm essentially taking K, copying it, and moving it somewhere else in G. So this is my visual understanding of K, and of cosets, and we have on our adventure sheet the definition of what it means to be congruent. So let's say x and y in G are congruent modulo K if x, y inverse is in K. But I think a more useful definition of what it means to be congruent modulo K is that x and y, maybe they're equally useful but for different purposes. X and y are in the same coset of K. You'll prove this, but let's explore this a little bit. So here, the elements A and K1A are in the same coset. This means exactly the same thing as them being congruent modulo K. In other words, they're in the same translated copy of K. And framed a different way, you could say that if I translate K1A into K by multiplying by the same element that I multiply EA by to translate into K. So to translate K1A into K, I would multiply by like A inverse. To translate EA into K, I would multiply by A inverse on the right. This is just another rephrasing of what it means to be congruent modulo K. Okay. I wanted to give this intuition. I'll say on your adventure sheet, parts C and D are sort of the meat and potatoes of what you're going to be proving. However, parts 1 and 2 are useful for getting there because you get some hands-on experience with creating your own cosets. Okay, thanks.